Hello, a great welcome to the series on Praxis. Myself Jalajan P. This is tutorial 4 and which will discuss the evaluation of a shear wall foundation in terms of settlements and stresses. In fact, this tutorial is developed in two parts, part 1 and 2. Part 1 discussed in detail about the soil structure and the mesh mode in Praxis relevant to this problem. In part 2, we will discuss in detail the simulation of the stage construction, solving this problem, and reviewing the results in terms of the settlements as well as the stresses. So let us start Plaxis. So we will start with the stage construction. So as you can see that the default initial phase is available to us right now, and in this phase Plaxis will calculate the vertical stresses as well as the horizontal stresses, which is just because of the surface of the soil. So if you just double click it, you can say that yes, we have used a K0 procedure for the calculation of the horizontal effective stresses, and all other parameters are applicable to us. So we don't want to make any changes here. So this is okay for us. And remember that in this initial phase, we want to calculate only the stresses due to the surface of the soil. So accordingly, only the soils will be activated here, as you can see that in the geometry also. So we have the soil volumes that is activated by default, and you can say that the beams, the plates, and the point loads are all inactive because our purpose is only to calculate the stresses to the surface of the soil. So now let us proceed to start a new phase. So add a phase, and let me just edit this phase. So I want to call this as a dead load plus live load, dead load plus live load, and this phase will essentially compute the stresses only due to the vertical loads. That is why it is labeled as dead load plus live load, and will straightaway calculate from initial phase, and all other parameters as in a particular the numerical control parameters will be set as default. We don't want to make any kind of a change or precision here, so this is okay for us. Now what is very important is that in this phase 1 module, we want to activate all the beams, right? And we want to activate all the plates, we want to activate all the point loads, okay? So now let us start defining the point loads in particular for this phase. So we want to apply the vertical loads only because this is a phase corresponding to the dead load plus live load. So only vertical loads will be applied during this phase. So let's just zoom this a little bit because we want to find out which point load stands for at which location. So for example, point load 1, we can just check it. You can say that yes, on activating and deactivating, this is point load 1. So here I want to apply a vertical downward load of 10,000 kilonewton. So I will keep it as Fz minus 10,000 kilonewton. Okay, and here we are not applying any kind of lateral loads. Only vertical loads will be applied at point 1. And now coming to point 2, let us see which is point 2. You can just activate and deactivate. You can say that yes, this is the location, point 2, that is corresponding to the column load location. And here I want to change the load. Actually, Plaxis has applied by default only a unit load. So this I want to change it to minus of 1500 kilonewton. So my point load 2 is over. And in a similar way, I want to change that point load 3 also, and let us change that also. So if you see, click and deselect, you can see that point 3 is this column load. So you can say, you can just apply this again, Fz instead of the unit load applied default by Plaxis, you want to change to minus of 1500 kilonewton. Okay, so this means that we have applied only vertical loads. That is, we have applied at 10,000 kilonewton here, 1500 kilonewton each at these column locations. This means that this phase is over, which includes only dead load plus live load. Now let us create two additional phases, one representing earthquake in x direction and the other representing earthquake in the y direction. Remember that this is my x direction and this is my y direction. Okay, so now let us just add another phase and just double click this. And remember, I want to start this phase directly from not from dead load plus live load. I want to start it from the initial phase, okay, because I am applying the total load corresponding to dead load plus live load plus wind load, sorry, earthquake load. So I will provide it with a caption of dead load plus live load plus EQX, indicating the earthquake shear applied in the x direction. and all other default parameters will be kept the same. Now here what we would do is that we'll just apply at this is phase 2. Remember, this is the model explorer for phase 2. So here at this location, what we do is that we'll apply, and in addition to F set, we'll apply in the X direction a load of 1000 kilonewton. Now you may ask me how this 1000 kilonewton is arrived. This 1000 kilonewton is applied so that we will have an applied moment of 1000 into 6, that's into 6000 kilonewton acting at the foundation level. This is the basis for the calculation of this shear. So Fx into 1000 kilonewton is applied, and we will not be changing the point load at other locations, which is essentially only 1500 kilonewton vertical, because we know that from our structural engineering knowledge, when we have got a very rigid mass here, and the columns will not be taking any shear. If at all they take, it will be hardly of the order of say maximum 5%, which is not considered in this example. So at 3 also, we have got only a vertical load of 1500 kilonewton. So which means that this phase 2 is exactly similar to phase 1, only that we have added a load of 1000 kilonewton in the x direction, right? So now let us define one more phase, especially for very specific to the earthquake in the y direction. So y direction means it is this direction, that's a shorter dimension. So let us add this. So here we'll just edit it, and we want to start this obviously from the initial phase, okay, and this will name it as, for example, for our easy identification, the load plus live load plus EQY. That's a quick shear in the y direction, and all other parameters very specific to the deformation control and the numerical control parameters will be kept as default selected by the PLAXIS. So this is okay for us. Now in this case, we want to ensure that in phase 3, that is dead load plus live load plus EQY, we apply a load in the y direction. So what we need to do is that we just press this point load 1, which is relevant to us. So in Fx it will be 0. So what we do is that this Fy we'll keep it as 1000 kilonewton. That means a shear of 1000 kilonewton is applied in the y direction in this particular construction phase. So this is okay for us. So this means that we have completed the staged construction, and basically our calculations will involve 3 phases plus an initial phase. Remember that in phase 1 we'll apply only vertical loads consisting of dead load plus live load. Phase 2 earthquake in x direction, and in phase 3 dead load plus live load plus earthquake in the y direction. So now we are ready to proceed to the to calculate the model and then review the results. So let us proceed to calculate the project. We press this calculate button. Okay, no nodes and stress points are selected for the curves. So we don't want to develop any curves for this project. So we'll just press ignore feedback and calculate. So as you can see that the calculation of the different phases are in progress. If you want to see the details, you can press this button and show the details. So let us start inspecting the various results. So as you can see that the best way to start any post processing review of the results is to start from the initial phase. So we'll start from the initial phase and we'll inspect whether the stresses are as expected. Okay, so what we do is that we have selected the initial phase over here. We'll go to the stresses and we go to the Cartesian total stresses. Here we'll select sigma z set. So as you can see that here it has shown the distribution of the stresses, and the maximum stress that is denoted is at the bottom, that is 360 kN per meter square. We know that this agrees very well with the calculated results, and we have assumed the water level at the ground surface. So accordingly, we can also have a look on the Cartesian effective stresses. Go to sigma dash z set. You can see that yes, it has reduced by 200 kN per meter square, which is equivalent to 20 meters of water depth. So the minimum value, that's 160 kN per meter square at the bottom. So this means that the initial stress calculations are in line with our hand calculations. Now we can easily go ahead with the other phases. So let us start with the first phase, which includes only the vertical load. So this is the dead load plus live load, that is a phase 1. And after phase 1, we would like to see the deformations. So we'll select, for example, the phase deformation, that is a rho uz. So P uz we have selected, that's a phase displacement. So obviously we want to calculate what will be the variation of this displacements within the soil. So the best way is to take a cross section that passes through the center of this raft profile in the longitudinal x direction. So we can do this by marking a vertical cross section by pressing this vertical cross section. So I want to take a horizontal cross section. There is a cross section passing through the center of this raft parallel to x-axis. So obviously what I can do is that I will call it as a minus, for example, from minus 40, this is 0, and the second point, this will be plus 40, and my y will be 0 again. So, so let's just, okay, so let us see how the variation, yes. So this gives you, let me just zoom it so that you will be able to see it in a better way. Yes, so this is the variation of the deformation, right, under the raft, okay, under in phase 1, which consists only the vertical loads, dead load plus lie load. And here you can see that the maximum displacement that is noted is of the order of 120.8 mm, and we find that this is basically maximum occurs right under the main shear wall, okay. So now, rather than this phase, we are interested in the two other phases, that is the phase earthquake X and earthquake Y directions. So I have selected earthquake X phase, that is a phase 2, that is a vertical load plus earthquake in the X direction. And this is how the variation of the stress, the variation of the deformations. Now, as you can see that this variation is exactly in line with our expectations, because here you will find that this raft has rotated in the clockwise direction because of the applied moment, and accordingly at the right under the right edge of this main raft we find that the deformations are maximum, and this deformation value is of the order of say it is so as you can see that it is a 120.8 mm, okay, as a 0.128 mm. So here it is 120.8 mm, and we can also see the variation of the stresses also right below this. And before that, I want to show you a plot of a deformed plot, or here there is a facility known as the cross-section curves. So what you can do is that you can also draw a line across this cross-section and see how the displacements or how the settlements or the foundation has varied across this line. So I will just press a cross-section over here. Now I will have a point somewhere very near to this, okay. I'll just draw a line somewhere up to the end of it, okay. Now as you can see that this right now it has provided you the variation of the displacements. Let me just zoom it so that you will be able to see whether the displacements are in line. Yes, you can see that here the displacements has increased because this is subject to a clockwise direction, and it is also possible for us to obtain the so-called cross-section curves. So we can have the cross-section curve here, and I want to see the cross-section curve, for example, only very particular to this phase, that is a dead load plus live load plus equiax. So you'll be able to see how the, so here look here, this is how the cross section. So you'll find that under this phase, so you find that the displacement it has progressively increased from 90 mm at one end, and is increased to the other end of this main raft to almost, say you can say that 120 mm, and away from the raft, and possibly this is the other end of the raft, where you will find that the displacement is minimum, the sediment is minimum is of the order of 70 mm, and then this is we are going to very near to the virgin soil. That's why we find that the displacements are small. So this is basically is the cross section contour of the settlement for the phase dead load plus live load plus earthquake X, right? So now let us go back. So I'll just have this, so I can so you can also see the window here. You can just do the tile vertically. So you'll find that yes, this is your cross section, right? So now we have already inspected this. So let us go back to this. So here again, we want to see the displacement right now. So now rather than earthquake in X direction, I want to see how the displacements will vary in the y direction for dl plus eq yy direction. So let me just select this eq y direction. Remember, this is your y direction. Okay, so select this eq y. Okay, and here I want to draw a cross section, a new cross section here. So I'll just draw a cross section, vertical cross section, and this time I will draw my cross section through the raft. So for example, I will have my x value 0, and I will keep my y value say minus 20, and this is okay, and this is a plus 20, so that I will be able to obtain how the deformation, how the settlement varies across this depth. So this is okay for me. So you'll find that yes, this is the cross section is now available ready for us. Let us just rotate it a little bit. Okay, this is okay for us. Let me just zoom it so that you'll be able to see it in a better way. Now look here, this is very beautiful. You'll find that yes, in the y direction, the rafters rotated in the clockwise direction. Accordingly, we find that the maximum settlement of the foundation is towards the right edge, and this is of the order of 156.8 mm. Okay. Now, just as we did in the earlier case, it is also possible to obtain as how the settlement profile of the soil right under the raft for this particular phase. So you can straight away go over this, then just press 2 points. So possibly I will select from this point to this point. Okay, so you'll find that yes, you just rotate this a little bit, rotate it a little bit. Okay, and if you zoom it, so you'll find that this is how the displacements have occurred, and it is also possible for us to obtain the so-called cross-section curve here. And another cross-section curve, I want to see only the earthquake in one direction, so this is okay for me. Okay, so now you look here how the raft has rotated. It is very clear for you. It has rotated like a rigid body, right? So, and at one edge, you can see that the deformation is of the order of say 90 mm, and to the other edge, it has increased to 150 mm, right? So this is actually is a peak deflected profile of this raft, which is also the deflected profile of the soil. And so this is all regarding the deformations. In a similar way, we'll be also able to see the so-called vertical stresses. So, and if you suppose that you want to see the vertical stresses, you can also straight away go, for example, I will take just one case, for example, in earthquake in y direction, or let me just say that how in the earthquake in x direction, how the stresses have changed. I will select this plot, and then I will go for the stresses, and I want to see how the total stresses have changed, or rather the effective stresses. Okay, let us start with the total stresses. So as we did, let us start with a cross section, with a longitudinal cross section. We'll go over here, we'll select it as, for example, x is equal to say minus of a 40, minus of 40, and with an x of a plus 40, plus 40. Okay, so now you will find that yes, this is how. So let us just zoom it a little bit because we are interested only in this portion. I can just rotate it a little bit over here. Okay, so you can see that how this is how the stress distribution variation has taken place. So we can also see a distribution of the stresses just by passing a line cross section across this. So just shift it a little bit down. So I'll start from this point and go up to this, and you will be able to see how the cross section, how the stresses have changed for phase 2. So this is the distribution of the stresses. We just rotate this a little bit. Okay, as expected, we find that the stresses are maximum just under the raft for this case, EQX case, and we'll also be able to see the cross-section plot here, tools, go to the tools and the cross-section curves. And I would like to see only, for example, the EQX here. Just okay, EQX. Okay, fine. So as you can see that yes, the stresses are maximum, that is of the order of say under the raft. It varies from 110. That means this is the main part of this raft. You'll find that the stresses is of the order of say 130 kN per meter square. And for the balance portion of the raft, you know that the stresses are lower. That ranges from say 130 to 110. And we are back to the virgin soil over here. So this is basically is the distribution of the stresses Okay, how the stresses vary across the line cross section that you have chosen. So this is how we need to interpret the results in terms of the stresses as well as the settlements for the various phases, and then find out whether these calculated values match with our design regulations. If not, we need to change the various parameters. For example, the raft dimensions. We need also to inspect how to improve the sort properties where we find that the settlements are very excessive. In this case, the settlements is of the order of, we have already seen, 100 to 150 and we to compare with the maximum settlement that can be tolerated by this shear wall building. So I think that we have reviewed the post-processing results in a better way. So that's all for this part. Till then, bye for the new tutorial.